Hello everyone, I am Anish from EC department. In the last video, I have explained you how to design a low pass filter, high pass filter, band pass and band stop. In this video, I will try to do one small application part of that thing. We'll take one small signal and we'll try to pass that signal through the filter which you have created previously. So in order to do this, you need to know about the filter command in the MATLAB. So what this filter command does is it takes the numerator coefficients and denominator coefficients from the digital domain, and if you give the x of n in the time domain, then that signal will pass through the corresponding filters function, numerator coefficient and denominator coefficient, and it gives the output in the time domain. So now you have got the output in the time domain. To check whether the corresponding frequencies are removed or not, what we will do is we will try to plot it in the frequency domain, and then we will use FFT shift to clearly understand which frequencies have attenuated and which frequencies are present till now. So if you try to plot the frequency domain, so if you only use the FFT, you will get the x-axis will be from 0 to n minus 1 into fs by n. If you use the FFT shift, then this will be changed from minus n by 2 to n by 2 minus 1. So if you use FFT shift, you will get centralized output, like around 0 it will be shown. If you use FFT, it will show only, like here you will get 0, and then here you will have the peaks. If you use FFT shift, then in between you will have 0, and at corresponding plus f1 you will have one peak, and corresponding to minus f1 you will have one peak. In case of FFT, if you have one peak at omega 1, the other peak will be at 2 pi minus omega 1, because the frequencies will be like overlapped in the FFT. So we'll plot the signal in the time domain, we will do FFT, and then we will do FFT shift for better visualization. So in the last video, we have seen how to convert from analog to digital. We had two methods. One is impulse invariance and bilinear. In this video, I have done using it in bilinear transformation. So as we are using bilinear transformation, we need to use pre-warping, and then we need to calculate the corresponding omega p, omega s of the low pass filter prototype, and then we'll convert the low pass to high pass, band pass, or band stop, and then we'll use the bilinear transformation to transform it from analog to digital. And after this process, you will get the numerator coefficient and the denominator coefficients in the digital domain, and these coefficients will pass through the filter command in the MATLAB, like nz, dz, and the x of n, and here x of n is in the time domain. And then I will discuss the effect of transition width on the corresponding filter, and we'll also see how to plot the frequency response in the analog domain itself. Like we have used bilinear transformation, so we had pre-warped in the first step. So if you want to plot in the analog domain itself, no need of pre-warping, it will be the step 1, and step 2 will calculate the num and n by using a Butterworth Cheby1, Cheby2, or elliptic. And the step 3 will be we'll use directly a plot command in the analog domain. Here, no need of using any bilinear transformation, because we are plotting the filter response, filters the frequency response in the analog domain itself. The only difference which you can see in the analog plot and the digital plot is, in the digital plot you will have the x-axis limits from 0 to pi, whereas in analog plot you will have the x-axis limits from 0 to infinite. So here it is not pi, it is not fixed. So in the last video we have plotted h of e power j omega, and plot in analog means we will plot h of j omega. So this is the difference. Here it is from 0 to pi, and here it is from 0 to infinite. So here I have written the MATLAB code for the signal. Here you can see I have taken cos of 2 pi f1, cos of 2 pi f2n, cos of 2 pi f3n, and I have plotted the corresponding frequency response. Only first I did with using FFT. Here you can see one is at let us say if it's at f1 10, and the other is at 2 pi minus 10. So for a better visualization, I used FFT shift. So here you can see if one peak is at 9, 9.48, which is approximately 10. The other is at minus 10, and one is at 50 and the other one is at minus 50. And we have used bilinear transformation. So we need to pre-warp first. So till here it is similar to the previous video. We have calculated the numerator coefficients and the denominator coefficients in the frequency domain after using a bilinear transformation. The new thing what we will be doing is using this filter command. Here I have given the numerator and denominator of the numerator and denominator coefficients in the digital domain and the x of n in the time domain itself. And I have plotted the FFT, and then I have done the FFT shift of the output, and I have plotted the corresponding output of the signal. So here you can see the passband is around 60 hertz and the stop band is around 70. So till 60 the frequencies will pass, and after 70 the frequencies will attenuate. Here the input frequencies are at 10, 50 and 100. So if we do this corresponding specifications for the low pass filter, so below 60 we have 50 and 10. So it should pass the frequencies below 50 and 10, and it should highly attenuate the frequencies at 100 hertz. So here you can see the red thing corresponds to the response after getting the filter from the filter command, and the pink color is the original plot of the x of n in the frequency domain. So here you can see the peaks corresponding to the 10 hertz and the 50 hertz are present, whereas the peaks corresponding to the 100 hertz are highly attenuated. And here you can check the whether the filter specifications is matching with our observation or not. At stop band I'm getting around minus 10 dB, which I required minus 10 dB itself, and at the pass band the attenuation is around 0, which is as expected. So next, coming to the designing of high pass filter, same here I have given the pass band 90 and stop band 60. So what it will do is after 90 it should pass, and till 60 it should highly attenuate. And if you check the filter specifications in the digital domain, at stop band I'm getting around a 50 dB, 50 dB, yeah, I'm getting around 50 dB, which is required. Here I have given AS equal to 50, that's fine. And around in the pass band I'm getting the attenuation around 0, which is still fine. And the same thing I have done here. I have passed the signal. Here you need to be careful while giving the numerator coefficients and the denominator coefficients to the filter. I have stored the output in NZ and DZ, and in the filter I'm giving the same NZ and DZ and x of n in the time domain. And I have did FFT and FFT shift, and here is a corresponding output. Here you can see the frequency peak corresponding to the 10 and 50 are not present. Only the peak corresponding to the 100 frequency hertz is passed through the filter. Here you can see I have plotted in the red. Red is like after getting the output from the filter corresponding to the Y, and the magenta, which is pink, it is of the original signal. So when you compare with the original signal, only the peaks corresponding to the 100 is getting passed, and the other peaks are getting attenuated. And similarly in the band pass, I have defined this 30 pass band 1, 70 pass band 2, stop band 1, 5 stop band 2, and 90 hertz. So here you can see in between 30 and 70 it will pass, and below 5 and above 90 it will highly attenuate. So in our signal we had 10, 50 and 100. So 50 hertz should be passed, and the other signals should be highly attenuated. So yeah, the corresponding plot is same. So corresponding to the 10, it is not passed through the filter. At the frequency which corresponds to the 50 hertz is passed, and the 100 hertz is highly attenuated. Similarly, for the band stop, I have defined stop band 1 as 30, stop band 2 as 55, passband 1 15, passband 2 90. So what this does is it will highly attenuate the frequency components which are present in between 30 and 55, and it will pass the frequencies below 15 and above 90. So according to our signal, 50 is in between 30 to 55. So it should stop the 50 hertz peak and it should allow the other. This is the corresponding digital frequency plot. Here you can see the attenuation is satisfied at the both stop band edges, and at the both pass band edges, the attenuation is around 0. And if you see the corresponding output after doing the FFT shift, here you can see the peaks corresponding to the 50 hertz are completely attenuated, and the peaks corresponding to the 10 hertz and the 100 hertz are passed through the filter, like are passed through the filter. And now here let's try to change the transition width of this bandstop filter, and let's try to see what happens. So here I am trying to change the passband one. So I'm keeping it as 20, and the stop band one is 30. Like what we did is stop band is here and passband is here. So initially passband was at 15. Now I have increased the passband to 20. So what happened is we have decreased the transition width actually. And let's run this code and let's see what's happening in the filter. So here you can see still it is satisfied. Now let's again try to reduce the width further. So I am keeping passband 1 as 25. So here you can see when I have decreased the passband 1 from 15 to 25, the transition width is very less now, because in the passband 1 to stopband 1 there is only 5 hertz gap. Here you can see the filter is not acting as expected. Here you can see there is some jumps in the graph, and here if you see, if you try to connect this line, somewhere we are getting the attenuation is less than required attenuation. So how can you understand this? What is happening in the filter? Try to pause the video and reason yourself. So yeah, let me give one example. Suppose you have end semester exam in 1 month. You have sufficient time. So daily you can prepare you can cover little syllabus, and then you can prepare well and write the exam well. And in the second case, you have end semester exam tomorrow, right? And you have only 1 day left, and you have a lot of syllabus to cover. So what you will do? Only less time is present. So till now you are in IPL mode, and now you have to shift to the study mode. The transition should take place within the less time. So what happens? If you are highly efficient, you can shift, right? You can study. But coming to the analog prototypes, they are not that much efficient. So that's the reason whenever you are trying to give the tight specifications like less transition band, that's the reason we are getting less than minimum attenuation at the stop band. So same case in the exam, you have 1 day left. You have to cover the syllabus. So time is completed. Now you have exam in 1 hour. Your preparation may not be to that level. Your preparation may not reach even a minimum preparation level of the exam. So that's what happening here. If you give the tight specifications, the filter is not reaching the minimum requirement level. So that's why we are trying to increase the transition band, so that we are losing the tight specifications. We are giving the filter sufficient transition width, so that it can attenuate slowly. So whenever it reaches to the stop band, it will do the sufficient attenuation. So just try to change this passband 1, passband 2, stop band 1, stop band 2 frequencies, and try to increase the and decrease the transition width, and check the response of the filter. So try experimenting with the transition widths and check at which values the filter is acting as desired or required. So now coming to the plotting in the analog domain, which we have already discussed in the slides. So here we are plotting in the analog domain itself. So no need of pre-warping. So direct values have taken and these values are given, and using Butterworth and Chebyshev we will calculate the num and n in the frequency domain. After calculating the num and n, here you have to be careful. Instead of using a frequency z command, here we are using a frequency s command. So this will plot the uh, frequency response in the analog domain itself, and then I have plotted the corresponding filters in the uh, analog domain itself. Here you can see at stop band it is around 50 dB, which is required minimum stop band attenuation, and at pass band it's around 0, so it's fine. So similarly for the high pass filter, I have done 70 pass band, 50 stop band, and I have plotted using f frequency s command, and I have done using frequency s command. Here everything will be same. Instead of using bilinear transformation, we will take the numerator coefficients and denominator coefficients and we'll try to plot in the frequency domain itself. And we'll try to plot in the analog domain itself by using a frequency S command. Here you can see at stop band the minimum attenuation is around 80, so which is required, and around pass band the gain is around 0, which is also still fine. And I want you guys to do similarly for band pass and band stop. Instead of using a bilinear transformation, just use a frequency S. That's it.